Hi, I'm Joe Agan, and I'm a member of the Fermi Science Support Center. In this tutorial, I'll show you how to do a bin likelihood analysis using 2 years of data from the Large Area Telescope aboard Fermi. You can find additional, more in-depth tutorials on the FSSC website. We'll be using a Jupyter notebook for this tutorial, but you could of course do all of this from the command line, or better yet, script most of these tasks. Most of the tools used here should finish in several seconds or a couple minutes, but a few will take much longer. You can run the whole notebook in non-interactive mode by hitting the Run button on the top menu. The total runtime on my machine was about 4 hours. Okay, we're ready to begin. First, we're going to need some data. Normally, you would go to the LAT data server at the link provided here and enter the information shown on the screen, and the data server would then extract the data that you need from the archive. You could also download the weekly event files from the FSSC, which contain events over the LAT's full energy range and covering the whole sky. For the sake of convenience, the FSSC has made a copy of the data we need for this tutorial that we can download directly from our website. The data we will be using covers the first 2 years of the mission and is centered on a source known as 3C279, which is a type of active galactic nucleus known as a blazar. We'll also select photons with energies between 100 MeV and 500 GeV. These first few commands will download the data and do some housekeeping to make the data files a little less cumbersome to work with. Okay, let's start running the Fermi tools. First, we'll need to select the events that we will use for our analysis. If your data files contain a larger parameter space than you need for a particular analysis, you can make sub-selections in position, time, and energy with the GT Select tool. You'll notice that many of the fields simply say in-def here. Since we already made these selections with our initial data query, we don't need to duplicate them here. Next, we'll run the GT MakeTime tool. We'll select events that are flagged with a data quality greater than 0 and collected when the LAT was in nominal data taking mode. These two tasks should complete fairly quickly. Next, we'll need to create a counts cube, which is a 3D counts map with one axis being photon energy. The spatial dimensions of the cube need to fit inside the radius of interest, or ROI, of the binned event file that we made in the previous step. So we make a 20 degree by 20 degree cube with spatial bins 0.2 degrees on a side. For the energy axis, we want 10 logarithmically spaced energy bins per decade in energy. So we'll choose 37 bins. The next two steps create a lifetime cube and exposure map. The lifetime cube is an array of lifetimes for a given inclination angle, and the exposure map accounts for the exposure on the sky in your region of interest. These steps together can take over 30 minutes to run, so doing them separately from the likelihood calculation will save significant time if you want to run the likelihood tool more than once. Alright, now we'll move on to creating a model file. This file is in XML format and describes the spectrum of the known sources within your ROI, as well as 10 degrees outside of it. We need to make this bigger than the ROI because the LAT has a very large point spread function, especially at low energies. So we need to account for the contributions of sources outside of our ROI in our analysis. To make the model file, we use a user-contributed tool called make4fgl.xml, which requires 4 inputs: the filtered events file that we created above, the 4FGL catalog file, and 2 files that describe the isotropic and galactic background. You can find the latest versions of the catalog and background files on the FSSC website, and your installation of the Fermi tools already contains the latest background files at the time of the release, so we'll just make symlinks to those. The output is a file called 3C279 underscore model.xml. Feel free to open this up with a text editor and have a look at its contents. The model parameters of 3C279 are shown here, so let's take a look at them. Right at the top, we can see that the source is located 0.7 degrees from the center of the ROI, which is expected, and that it is also referred to as 4FGL J1256.1 minus 0547, which is the name of the source in the 4FGL catalog. Next, we see that the source spectrum is described by a log parabola function, with the values for the different components of this function corresponding to 3C279 filled in below. And finally, the right ascension and declination of the target. These values were taken from the 4FGL catalog that we gave as inputs to the make4fgl.py tool. We also see that some parameters have the free field filled with either a 1 or a 0. A 0 means that the parameter will remain fixed during the likelihood analysis, while a 1 will allow the parameter to vary within the min and max values listed on the same line. So here it's important to note a few caveats. You can manually change any of these parameters for the free field from 0 to 1 or vice versa, but care should be taken when doing so. Many sources are significantly variable over time in both intensity and spectral shape, so the average values taken from the 10-year source catalog may not be accurate for the time period you are analyzing. However, leaving too many free parameters has its own downsides, including increasing the time it takes to perform the likelihood analysis, and this can be done to such an extent that the likelihood analysis cannot be completed. So, it's recommended that you take some time to explore the XML model file, as well as the options of the make4fgl.py tool. You may need to adjust your model file several times before you get a good fit from your analysis, so becoming familiar with this process will come in handy later. The next tool, GT Source Maps, creates a model counts map for each source in the XML model file. This will likely take several minutes to complete. The last step before we run the likelihood tool is to use GTDiff.RSP to compute the diffuse responses for each of the diffuse sources in our model. This is a very computationally intensive step and can take several hours to complete. Okay, we finally have everything we need to run the likelihood analysis. The tool that does this is called GT-like. There are a lot of options that you can use with this tool, and you'll probably utilize many of them when you do your own analysis. Please feel free to check out the various analysis threads and other documentation that we have on the FSSC website at fermi.gsfc.nasa.gov. For now, we'll use the input files that we created above and select the new minui as our optimization algorithm. This is another tool that will take a while to run. You may want to start it before you head out for lunch or home for dinner. And by virtue of having run this tool already, we can see that we have results. The source was described in our model with a log parabola function, and here are the values for the various parameters of that function, along with the errors in the first and second columns here, respectively. You can also return a quantity called the test statistic, or TS value, for each of the sources that were fit in the analysis. A TS greater than 25 is generally considered to be the threshold for a strong detection. As 3C279 was a very bright source during this 2-year time period, its TS value is quite a bit higher than 25. Since we're already in Python, you can also call other packages such as matplotlib to display the results graphically. Here you can see a plot of all the different sources in our model file with the cumulative count spectrum at the top with the detected data overplotted. And here you can see a difference plot, counts minus model count, detected counts minus model counts divided by model counts. You can see that the fit is very good at low to medium energies and maybe not so good at higher energies. The next step in doing an analysis like this would be to check for convergence and modify the inputs to GT-like as needed, specifically by modifying your model file until convergence is achieved. More information and helpful tips on this topic can be found at the FSCC website. And that brings us to the end of this tutorial. Thanks for watching.